Okay, so yeah, today let's talk about the uh class math. Um okay, um so actually um okay, yeah, so last time I think I showed that there is a local biholomorphism for the yeah, so yeah, actually last time I think I showed that this gammas of gamma is actually a universal holomorphic coloring, sorry, a holomorphic universal coloring map. Okay. Um, uh, okay. So, and then let's continue. Okay. So then, um, okay. Okay. So then, um, where is the, oh, shoot. Oh, oh, here. Okay. Have it on the backpack. Okay. All right. So, some calculus notes. Um, okay, um, so in fact, so we have that this gamma uh oh sorry, so it should be uh, the universal covering map. The uh, uh, gamma um has associated that transformation group that is gamma equal to the gamma, which is contained in the uh that transformation B of uh sorry of the common space map. Yeah. Okay. Um because uh because the split gamma is contained in the that transformation B of this of the uh division by n. Okay. So this common map divided by defined by you just divide the Z by M for the common space map. Uh, and for any point Z in C, gamma acting on Z is equal to Z plus MZ. Sorry, it's the integer Z, which is equal to the uh so I will call the rescale exponential map. Okay. So of the sorry rescale exponential map inverse of the rescale exponential map of Z. So oh okay. So yeah, this is just like so this is like showing that why this so why the space uh so why the quotient space is wait so yeah so remember that we have two things, right? So one thing is the exponential map uh, uh yeah so yeah so one thing is that we have the rescaled exponential map uh which is usually defined as uh z goes to e to the 2 pi I c over m. Okay. So on the one hand, we also have the space that's once you have a user calling space, and then you can always and then you have a subgroup that is uh, properly discontinuity. Sorry, a subgroup of the automaton group that acts properly discontinuity on the user calls. So there is you can induce a quotient space, right? So you can induce the quotient space uh, by the quotient of the orbit of this gamma. Okay. So yeah. So actually, we want to show that why these two are the same. Okay. So um, okay. So let's see why this the data transmission group of these rescaled exponential map is equal to gamma, which is the group gamma. Okay, so what is exactly the group gamma? So what is the definition of the group gamma? Um, oh yeah. So remember that we defined. So we have what we have argued that uh any group gamma must be the form MZ as a subgroup of Z. Okay. So this gamma just equal to the group gamma is just equal to MZ as a subgroup of Z. Okay. Uh, yeah, so we have already identified so why this stack transformation group of this. Okay, so okay, okay, so here basically uh yeah, so for this universal covering, so it has uh so I want to say that it has the associated dextran contribution group as empty. Okay, so why that's true? So because uh so why that's true? So why the depth transmission group of this one is exactly the empty. Um I think you can also build a map between the usual uh so remember how we build a map between the dash. So let's just forget about this gamma for gamma. So remember how we build a uh relation between the dash transmission group and this z, right? So namely, what we do is that uh okay, yeah. So let's do that. So I think we start with this. Wait, is that an injection or by injection? I think that's the other way, right? So we start with z and then we map any element z to the map phi naught n, right? Where this map is being defined as v goes to z plus n thing. Okay. So yeah, we show that this is a we show that this is a so we show that this phi zero n is actually a depth transformation group of this gamma, right? Because first it's continuous homomorphism, and then after you compose you compose it with yeah, so you write let's compose with this one, and then let's even the same, right? Why it's the same? Because if you plug in any z, then it becomes z plus n, and then after okay, because this a is being added to x. Okay, therefore after you apply the e to the 2 pi I to the x value added by n. So yeah, because it's the same. Okay. So um okay, so okay, so let's construct the other way. So let's see if we do the plus in m. So let's change it to m here. Let's show that this is actually a that transformation group of this one. Okay. So why is it true? So let's say that if you compose this one with our file sum m n, let's see whether that's the same as uh exactly the map. Okay. So okay, so let's see if you plug any z into it, test it with a z. So on the left-hand side, you will have huge gamma of the phi mz, which is z on n. So which is exactly if you grade it in here, is e to the 2 pi I of z over n, which is z plus n m over n. Okay, so and then on the right hand side, you will just have so Okay. So then, okay, because yeah, so this m actually cancelled out, right? So on the one side you have d over m, which is the same. Then you will have plus the m just exactly n, and then this one you just like the inner circle wraps around. So actually two are the same. So because z is arbitrary, so therefore these are equal. Okay, so I think now we show that this is a so it is a homomorphism. So I think it's also a homomorphism, right? So okay, so yeah, so that shows that this is actually a next dimension group of this map. So we get one direction, right? So we get one direction from uh so what is one direction? Okay, so wait. Um let's see. So uh oh yeah. Yeah. So because element in this MZ are exactly n times n, right? For some n in Z. Okay. Maybe I'll use Mn. Okay. Um yeah, so we show that it is uh wait, which way am I going? So okay, so I show that at least it is a injection, right? Injection map. Uh why is it injected? Uh because uh also let's say for any okay. Because if you have one unit inductive, so the map MZ goes to okay. So what is really map? The map is from MZ to phi of MN, where this M is exactly the so MZ okay, MZ oh MZ so MZ is like neutral powers of M, right? And then this guy is also because this M is fixed, right? This M is fixed. So the only thing that's changing is at the end, right? So basically, if you have, let's say, so why is it rejected? So in order for you to check rejected, okay, so maybe I will say, uh, instead of mapping it to this space, so let's map it to just uh uh how do I write it? So uh yeah, so maybe I think it's better for me to just write the Yeah, for the space mapping. Okay, for the space mapping, please map onto the space, the depth transformation group of this space. So if you have two map, okay. So if you have two map, so suppose that this map is like this phi. So if you have phi of uh like uh n1m equal to phi of, okay. Yeah, I think it's trivial. Okay, it's trivial. Okay. Anyway, so um okay, so y is onto. Okay, so y is onto. So okay, so I think wait. I think the ontoness can be shown by exactly the uh so y is onto. So uh okay, so remember that have a for any, okay, so what do you want to show? So I want to use the argument about I want to use the corresponding argument about the depth transformation group and the correspondence between the depth transformation group and the pi one, right? So what is the pi one that I want to use? So here, okay, yeah. So here, it is the coordinate map, right? And we are mapping onto the same space, which is also the C star. So why is it just C star? Okay, yeah, it's just C star. Okay. And then, uh, okay, so this is a, we show that it is a universal covering map, right? Yeah, we show that. So therefore, by the theorem we have, we know that there is a correspondence between the chi one of C star, uh, let's say and zeta naught. Okay. And also the depth of the, wait, I was a little bit confused. So because the C1 is pi one is the same, right? So does that imply that these two depth transformations are the same? I don't think so. So where did I put, where is the wrong thing that uh yeah, let me check the book. So I'm checking the chapter 10. So for the chapter about the depth transformation, um yeah, sounds mm, So so okay, I know that for the universal cover, right? So the universal cover is unique after uh yeah after equivalence relation of covers. So what is the equivalence relation of covers? So the equivalence relation of cover is so any two covers is of a same topological space X. They are equivalent if there is a homomorphism that is a lifting. Okay, so why? So yeah, maybe I think I'll just pause it here. So maybe I'll so maybe let's say why. Yeah, otherwise I think another yeah, the next uh yeah. So what's going on here? Uh wait. So this gamma is exactly MZ, right? Okay, so I don't think that's really a contradiction here because so this is just MZ, okay. Um okay, so what there is a one-to-one correspondence between this part one and stack transformation rule. By just you do a uh yeah, so it's basically by the same mechanism. So you have the gamma and then yeah, so the gamma is actually being lifted to the point where you have the Z naught and then you're having Z naught plus M, I think, right? Um So why is it mapping here like that? Uh, okay, so you can construct this gamma, little gamma tilde of zero. I'm sorry, the little gamma tilde, right? Um, okay, and then you show that this part one is infinite cyclic group generated by um. Okay, so this is now. So just imagine that you take yeah, imagine that you take because this is like the yeah, so because these elements they are the element of the diagonal group of respect to this, right? With respect to the gammas of two gamma. And then you take this n to be one. So therefore you get a map from z to z plus n. And then you plug in the base one. So then you get so you specify the uh yeah, so you specify uh, the mapping at the now, right? Uh, okay. So because yeah, okay. You specify the point at the node, and then that will give you a map. Uh, wait. Yeah. So that corresponds to a element of part one. Okay. Which which is what? So which is exactly the projection, right? The projection of this path into here, right? Because under this map, yeah, under this map, because this map is exactly if you replace d dot by d dot plus n, that will give you the same thing. Okay. So okay, so let's see. So right now, uh, okay, so uh, wait, so so uh, okay, okay, so okay, so I think in this case, okay, never mind. So this now is actually e to the two pi I z naught over n. Okay, actually, yeah, okay. So then we'll replace this d naught by d naught plus n. So yeah, d naught plus n. So what you do? So uh, okay, yeah. So that will be a loop. Okay, that will be a loop. Okay. So and then um. Yeah, so by the same argument, right? So by the same argument that we did before for the lifting, you get a constant here and then the lift. And then so then now what? Now Oh, yeah, because it's a one-to-one correspondence, right? So, shoot. Okay, so I want to show that. So for this element, right? So this element is an element in this part one, right? So therefore, I want to show that. Okay, so under the map, because for the covering space theory, there is sorry, for the first theorem we proved for the deck transformation group, there is a one-to-one and onto correspondence between the oh, wait. Uh, wait, what I'm trying to show you here. Uh, okay, I think maybe let's control this. Okay. Um, okay, so yeah, so I will show that this is a injection map. Okay. So I want to say why it's a surjection map. It's a surjection map because uh uh so why it is surjective? Because for any uh uh oh any element of the deck transformation group uh can be uniquely identified by this uh why is this subjective? Um okay, so you have the element of this part one, right? So we show that this part one is actually uh so oh no. Okay. So we can map this, yeah, we can always map this part one element of this part one onto the deck transformation group by this view. Okay, by this view. So okay, so uh I think there's a what about the uh the generator. So what is the generator here? So um okay, okay. So for any element of this stack transformation group, right, we can specify it by just saying that, okay, yeah. So for any element in the stack transformation group, we can always specify it by the initial value, by its image, by the image of this value, right? So yes. So what are the possible image of this value? Uh, so what are the possible image? Okay, so the possible image are actually contained in the inverse of this Z naught. Oh, sorry, of this zeta naught, which is okay, so which is this one, right? Okay. Yeah, so what are the possible image? What are the possible pre-image of this point? Um, okay, so this one is actually um e to the 2 pi I z naught over m, right? So um so what are the possible pre-image of this one? Um okay, so what are the possible pre-image? So for any z, um so I want to claim, let's claim. Let's claim is mz is equal to so let's claim is so let's check it. So for any z is yeah. Uh so I think the left hand side is trivial. Okay. Yeah, so because if you take the e to the 2 pi I z, you just replace sorry. So you just replace z by z naught plus m mn, and then uh yeah, so and then becomes yeah, so that's the same as uh Uh, that's the same thing as, yeah, that's the same thing. Okay, so let's show the other way. So let's show that if you have G in this image, right? So it implies uh, e to the 2 pi I c over m is equal to e to the 2 pi I c naught over n. Okay, so okay, so this implies what? So this implies e to the um. So let's suppose that this is e is equal to x plus iy, right? So e to the 2 pi I x plus iy uh let's say over let's see over m, which is equal to the 2 pi I uh times y I naught over m. Sorry, I y naught over m. Um okay, so this is okay, so for the left hand side, this is equal to um so for the e to the 2 pi I x over m. Okay, so this is the argument part. And then times e to the minus, so 1 over e to the 2 pi y over m. Yeah, so this is the real part. And then so from here, so we get, so this is what? So this is just e to the 2 pi I x naught over m. So imaginary part times e to the, so 1 over e to the 2 pi y naught over n. Okay, so this is the real part. Uh, okay, so then by definition, so the right hand side is equal to so this is exactly uh cosine of 2 pi I x naught over m. Okay, so comma sine of x naught times e to the uh 1 over 2 pi y naught. And then same thing here. So this one is equal to cosine of uh 2 pi I x over m sine of 2 pi I x over times the 1 over 2 pi 1 over n. Uh, so why these two are the same? Okay, so I know that these two are the same. Uh, yeah, I know that these two are the same, right? Um, So if you have sine of this angle, uh, so let's see. So yeah, so these are equal. This implies that uh, okay. So uh, okay. So So for the also X over M. Uh, some echo. 最好这个 think that I think we can get the sine of this one is equal to cosine of this one plus power two, right? Uh, well, so therefore, if you have the cosine of this point, which is equal to uh cosine of this one times the constant number, okay, and then this one plus power two is equal to this one plus, so this is also equal to cosine of 2 pi x ln m plus power two. Yeah. So yeah. So uh, it must be the uh, so this one is just two, either two values. So on the other hand side, you are moving towards left by power 2. And then I claim that that's equal to the same thing as moving right by power 2. So if they are not the same, then so move to that right. So take another point. So this just says that the cosine of 2 pi x over m is equal to the cosine of 2 pi x now over m times the same number, right? Uh, times this number. And then this is saying that the sine of, sorry, the cosine of, so basically this thing that you, if you increase by this one, right? Then you will increase by the proportional amount. Yes. So, um, increase by the proportional amount. Uh, uh, okay. So this means that if you take this flight and then you are taking this point, their ratio is this constant. And then for the left hand side, uh, okay, whatever, you choose the smallest one. Okay, so you choose the smaller one. And then uh, for the left hand side, you add by like, yeah, so you add by a value of power 2. Okay, so, and then on the right hand side, you also add like by the same value. And then it's saying that uh, their added co- their added quotient is like the same. Yeah, it's like same. Same, yeah, yeah, same. The quotient are yeah, it's the same. Yeah. So why? Uh, I think the idea is that um, so say that there is like uh, okay, so for this guy and this guy, there is a smaller number, right? So let's suppose that this one is a smaller one. Okay. So yeah, so uh we put the smaller one like and then okay and then so then their difference is like um uh okay so say that these two points they uh let's say that they both lie in the first like first one first quadrant, right? So sorry, the first one first piece, right? So from 0 to power 2. Okay. So when you increase, we will increase by power 2. So then so this is like the let's say that this is a smaller one, which is the let's say cosine of 2 pi. This corresponds to the x. Okay. So this is actually bigger. And then and then if you let's say uh divided by the smaller one. So this is actually smaller, right? because the y value of this one is smaller. So this one is bigger than one. Okay. So then if you add it by like a power two, right? So then we add it by power two. So actually this one becomes smaller, and then this becomes negative, right? So this becomes negative. So both become negative, but so therefore, yeah, so therefore the difference kind of yeah. So the negative sign is gone. So and then but for the absolute value, this one will be uh small. This one will be big. Suppose that they are not different. Okay, so suppose that they are different. So this small is big. So actually the quotient will be less than one. Okay. So let's see. So suppose you pick another. Yeah. So I'm just trying to say. So this argument work. This argument works for any. So for the any of the other point that lies like after this one, right? So uh suppose that it lies in like here. Let's see. So if you add like another point, let's say you add another power to here, then uh okay, so this becomes that. Then they cannot even be the same because if you start with wait, yeah, you cannot start here because if you start here, then if you add power two, because the initial ratio will be positive, will be negative. And then if you add power two, then it becomes both becomes negative. So the ratio is positive. So we cannot have the starting point that lies at this interval. Okay. So what about this interval? So for this interval, if you start here, yeah, and then uh the you will have the two ratio as so actually let me see. Uh if you start here, so namely you are adding a pi to it. Right. So namely you are adding a pi to it. Can anything say? Actually, I think these are the same because if you add power to then that. Um, Okay, yeah, shoot. I think the ratio couldn't be negative. Okay, because this is positive. Okay, and this is also positive. So their ratio cannot be negative. Okay, so therefore you cannot start here. Okay, you start at this point at the center point zero. I don't think so, given that because this point is all positive, right? You can have zeros. So can you have yeah, you also can have zero here. So these points are yeah, so you can have here because you add power two, then you hit a zero. So this one you cannot start here. Okay. And so what happens if you start? Okay, never mind. So uh yeah, what happens if you start here? So and yeah, so this will be zero. So um and this will be zero. And so what about zero? Okay. Okay, let's continue with the original one. Let's say that start as something that's not towards that. Oh, I think they are the same situation, right? Yeah, so there's nothing different from the previous analysis about whether we start here or we start the zero here. So yeah, so let's see whether we can start. Yeah, we cannot start here as well. Okay. So and then what about starting at here? Starting at the the last part. So if you start the last part, then um the sign doesn't matter, right? So yeah, so if you start the last part, then uh the sign usually will cause you trouble because after adding a power two, then this sign becomes negative. And also this point becomes still positive. So therefore you cannot also start here. Okay. So let's say that whether yeah, so for the science issue, right? So let's say that if we start here, is there still a sign issue here? Um, let's see. If we add like uh, if you start with Okay, so if we start with uh, oh, okay. So if you start here, then you cannot start. So the second one you cannot start anything that is not at this uh because the second point, if you add like a power two, then this lies in is equal to zero. So this means that you have to start with something that after you add power two becomes zero, right? So either you start here, which they just trivially holds, and then you can also let's say start here. But if you start here, then the first ratio will be negative, right? So it's a contradiction. So then you may start, oh, okay. You start here, then you cannot start here because otherwise the first ratio will be it will equal because this side is not zero. Okay. So then you start here, which is fine. And then you have to have another 2 pi being added to here. Okay. So the only choice, so if you start here, the only two choices are exactly the same point or like a 2 pi added to it. Okay. Okay. So then you may wonder, uh, okay, okay. I think the same analysis still applies to the rest, right? Um, so let's say, if you start with, um, so if you, uh, okay, yeah. So if the bigger one start here, like the bigger x values. Oh, sorry. What I mean is that I mean the smaller x values. Okay. So small x values start here. Then let's say that we have this point. Um, yeah. So then we can the starting point must be one of the 0 points, right? So that is either here, which cannot be because the sign is different, right? And then here, no, because okay. So then I think this is the only point or plus 2 pi. Okay, so if you start here, then uh can you start somewhere here? Okay, no, because the sign doesn't matter. The sign is not the same. Okay, so I think we have reached a conclusion where uh either right. So either if you start uh yeah, so we cannot actually start with the same like uh, uh yeah, so we cannot okay, so anyway, so if you start here, cannot because the sign is not the same. Okay. And then if you introduce the other one to here, then 2 pi to power 2 to it. Um, From there. So the only two possible points are uh, um, this one is about, yeah. So you start here, then uh, must be next. You must be start with, yeah, so we can't. You start here, then you start. The only one is here. Okay. So I'm learning to part. Yeah, so actually, yeah, so we saw that it's small, real small. Yeah, so it's fit. So yeah, so I'm convinced by the uh like some starting point and point analysis. So okay, I believe that there are various methods that you allow you to show that these 2 points x and x naught either they are equal or they make there's a difference of 2 pi. Okay, so that shows the uh argument, I think. Okay, so uh they either equal or they differ by at least some copies of 2 pi. Okay, or this uh 2 pi x naught over m. Okay, so for this oh sorry, I didn't describe that. Okay. Uh, it's equal to this one plus 2 pi n. Okay, so where this 2 pi n you can rewrite it as uh 2 pi n m over m. Okay. Okay, so I think that's the proof, right? So uh this implies that um after we divide by 2 pi and then multiply by m, so therefore x equal to x naught plus m. So then you may wonder what about y? Uh okay, so yeah, so once we have that, I think we can just show that these two values are the same. So therefore the y value must be the same, right? Because the exponential is a injective function. So uh yeah, so therefore that shows this result. Okay. All right, so that's the proof. Okay, so let's continue next time.